Alright, hello, this is group number 1 for the final 3600 project. My name is Ben Coombs.
I'm Joshua Dunster.
I'm Jonathan Sarasua.
And I'm Megan Fowler.
And we're going to show you how awesome our new implementation is. So let's start our robot server. This is the newly modified one that we changed, and we'll start timing our robot client. So our robot client and robot server interact very differently than the old one. The old one uses stop and go behavior, so the client would send data to the middleware, and the middleware would send that data after translating it to the robot server. And then the robot server would send the data back to the middleware, which would then send the data back to the client. And then the client would send the next command. So as you can imagine, this is a very inefficient way to process all of the commands and data transactions. In ours, we send all of the commands at once, which you can see in the packet printed out in hexadecimal here. And then the server is in charge of processing all of those commands. So when we ran ours, we got a real user time of 38.6 seconds. So now let's end our server and start running the former implementation. Now we use threads in the server to make efficient use of the program time, especially when we're waiting on the robot to move. And Jonathan can talk a bit more about that.
So with threads, we wanted to have continuous uptime where we send messages continuously to the robot from the middleware server. But we also wanted to be able to send messages to the client while we're waiting for a response from the robot. And the best way to do this is with threads. So we have a thread for the send receive robot function, which does all the communication with the robot, and then we have a thread for sending messages back to the client. And then we have another thread that just handles messages from the client. All of this works seamlessly with queues, and it's kind of like a factory.
Right, and so you can see the effect of that here. We have a real user time of 43 seconds approximately for the old code that we did not modify. And for ours, we have a real user time of 38.6.
Which is about a 13% increase, or 13% reduction in time.
Right, so we have a speed up of about 1.12. And we're measuring good put with the total program runtime because we also use compression, and that makes it difficult to measure the good put with data sent across the wire, since the compressed data is more informationally dense than the uncompressed data. But assuming that the client does the same commands for the given input, then the same amount of useful data in terms of image and text files will be transferred for each runtime of the application. And we think that this is a sufficient way to show that good put is much better for ours than Brett George's. You want to say anything about compression?
Yeah, the compression algorithm we used was just a pretty basic dictionary approach. It would look through each string that we wanted to encode and try to find a lot of strings of 4 bytes in a row that were repeated about 6 times at the least. And that we judged was about as many times as we would need to get a valuable reduction in the amount of information we needed to store that file. And we mostly use this on the image files because we could see that, especially if the robot was off of the screen or the out of the areas of the field where other robots were, there wasn't very much extra information throughout the image. So you can tell it's kind of just a blank screen or blank gray canvas. So that really got us a good reduction in the number of bytes we really needed to store each image.
Right, so I think that covers the main architecture of our program. The most important thing we did was making sure that everything was managed by a single program, which could then efficiently allocate time so that while we're waiting on the robot to move, we can be doing things that matter, such as sending data to the client, which can then take care of the data processing and other things like that. I think unless anyone else has something to add, that should be the conclusion of our video.
Bye.
Bye-bye.
Thanks for listening.
I mean, that was